7 miles below the Pacific, there is a wound in the planet so deep that Mount Everest could vanish inside it with a mile of black water still on top. The United States Navy has the technology to map it. They have not. 3/4 of this trench has never been scanned in detail. Down there, hydrophones record sounds nobody can identify. Submarines implode before reaching the floor. Creatures swim through pressure that would crush a tank. If you enjoy real ocean mysteries, hit subscribe. It helps us keep going. Take a breath. We are descending now. In 1998, a Japanese research vessel called the Kaiko was making one of its routine descents into the Challenger Deep. It carried cameras, sample collectors, and the usual array of scientific instruments. The team on the surface was hoping to film deep sea creatures and collect sediment from the seabed. What they filmed instead became one of the most famous images in deep sea research. A plastic bag, ordinary, white, crumpled, sitting on the bottom of the Mariana Trench at a depth of about 36,000 feet. The image traveled around the world. People saw it and felt something they had not felt before. The deepest place on Earth, a location only a handful of humans had ever visited, contained trash from a corner store. The bag had probably been thrown away decades earlier, somewhere on land. It had floated into a river. It had drifted out to sea. It had eventually filled with water, sunk, and drifted slowly downward through every layer of the ocean. After years, possibly many years, it had settled at the bottom of the deepest trench in the world. It was not the only piece of plastic in the trench. Far from it. Researchers have been finding plastic at the bottom of the Mariana Trench on nearly every expedition that has gone down to look. Plastic bags, plastic film, pieces of plastic packaging, microplastic fibers embedded in the sediment. The entire deep ocean appears to be slowly accumulating plastic from the surface, and the trenches, as the lowest points, are receiving more than their share. A study published by Japanese researchers used data from over 5,000 deep sea dives to estimate the total amount of plastic on the deep ocean floor. The numbers are sobering. The deepest places contain higher concentrations of plastic per square mile than many shallow coastal areas. Why? The trench acts as a natural collection bowl. Plastic that drifts on the surface eventually loses buoyancy and sinks. As it falls, it tends to drift toward the deepest points, where the underwater currents converge. The bottom of the trench is, in a sense, the lowest point in a vast slow-motion drainage system. Anything that sinks long enough eventually arrives there. The plastic does not break down. Not really. In the cold and the dark, away from sunlight and oxygen, plastic decomposes extraordinarily slowly. A plastic bag at the bottom of the trench may sit there for hundreds, possibly thousands of years before it begins to fragment. And when it does fragment, the pieces become microplastics, tiny shreds smaller than a grain of rice. The microplastics are then eaten by deep sea animals, including the amphipods we already met, who mistake the particles for food or absorb them while feeding on contaminated sediment. Researchers studying amphipods from the Mariana Trench found microplastics inside the bodies of the majority of specimens they tested. In some samples, every single individual contained plastic in its digestive tract. The deepest animals on Earth are eating us. What this means for the long-term health of trench ecosystems is unknown. The animals appear to survive with the plastic inside them, at least for now. Whether their reproduction or population stability is affected by chronic plastic exposure has not been fully studied. The trench is hard to access. Long-term ecological monitoring at extreme depth is in its infancy. What the plastic discoveries have done is destroy any romantic notion that the deep ocean is a pristine wilderness untouched by human activity. The trench is not untouched. It is a sink, and it is filling. But plastic is only the most visible kind of contamination. The chemical kind is worse. The amphipods of the Mariana Trench had a secret in their tissues. and it took until 2017 for researchers to fully expose it. A team led by scientists at Newcastle University in the United Kingdom collected amphipod samples from two of the deepest trenches in the world, the Mariana Trench in the Pacific and the Kermadec Trench, which lies northeast of New Zealand. Both trenches are over 30,000 feet deep at their lowest points. Both are far from any major industrial activity. Both should have been, in theory, among the cleanest environments on Earth. The team brought the amphipods back to the lab and measured the chemical content of their fatty tissue. The results stunned them. The amphipods contained extraordinarily high levels of a class of chemicals called persistent organic pollutants. These are human-made compounds that include polychlorinated biphenyls, known as PCBs, and a group of flame retardants called polybrominated diphenyl ethers. These chemicals were widely used in industry during the 20th century. They were used in electrical equipment, in coolants, in plastics, in industrial coatings, and in furniture treatments. Many were banned starting in the 1970s because of their toxicity. But banning a chemical does not remove it from the environment. The persistent organic pollutants means exactly what it sounds like. These compounds do not break down quickly. They linger for decades. They drift on currents, settle on particles, and travel around the world. The levels of PCBs in the trench amphipods were comparable to those measured in some of the most heavily contaminated industrial bays in the world. In some samples, the concentrations were as high as those found in shrimp, from rivers downstream, from polluting factories. That is the bottom of the Mariana Trench, the deepest, most remote habitat on the planet, carrying chemical fingerprints of factories that closed before most living humans were born. The mechanism is the same as everything else we have already discussed. Pollutants in the upper ocean attach to organic particles. Those particles sink. The trench collects them. The amphipods, scavenging at the bottom, accumulate the chemicals in their fat. Because amphipods live a long time and feed continuously on contaminated material, the concentration of pollutants in their tissues builds up over years. Larger predators that eat the amphipods then accumulate even more. This is called biomagnification. Each step up the food chain, the chemical concentration rises. The deepest fish in the trench, including the snailfish, are likely carrying significant chemical loads in their bodies as well. The discovery rewrote the textbook on deep sea ecology. It demonstrated that human pollution had successfully reached every habitat on Earth. There was no place left where ecosystems were free of industrial chemicals. Not even 7 miles below the surface, in a place fewer humans had visited than had walked on the moon. The implications are still being studied. Persistent organic pollutants are known to disrupt reproduction in many species. They suppress immune function. They can cause developmental abnormalities. Whether they are doing the same thing to deep sea creatures in the slow and isolated dark of the trench is not yet clear. What is clear is that the trench is no longer just a geological mystery or a biological frontier. It is now also a chemical record of the industrial age. The deepest place on Earth is documenting our history, one polluted amphipod at a time. And the trench is not just collecting our garbage. It is also generating its own kind of violence, the kind that shakes entire continents. The Mariana Trench is not just a hole in the ocean floor. It is the active edge of a slow-motion collision between two of the largest tectonic plates on Earth. The Pacific Plate, on one side, is being pushed northwest by forces deep within the planet. The Mariana Plate on the other side is the smaller plate getting in the way. Where they meet, the Pacific Plate dives downward, sliding underneath the Mariana Plate and into the molten layer below. This process is called subduction. It happens at every deep ocean trench in the world. It is what creates the trenches in the first place. Subduction is also one of the most powerful sources of earthquakes on the planet. As one plate slides under another, the rock does not move smoothly. It catches. It sticks. Pressure builds for years, decades, sometimes centuries. Then the rock suddenly slips, releasing all the accumulated stress in a single violent event. The result is an earthquake. In subduction zones, those earthquakes can be enormous. The Mariana Trench is one of the most seismically active places on Earth. There are thousands of detectable earthquakes in the region every year. Most of them are small. Many are too deep or too distant to be felt by anyone on land. But the trench produces them constantly, like a slow drumbeat under the Pacific. The really big ones, when they happen, are terrifying. In April 2016, an earthquake of magnitude 7.7 occurred near the southern end of the Mariana Trench. The epicenter was almost 200 miles below the seafloor, in the descending Pacific Plate. Earthquakes at that depth do not usually cause much damage at the surface. The energy is absorbed by the layers of rock above. But the magnitude was large enough to be detected by seismometers around the world. What is striking about this and many other Mariana earthquakes is that almost nobody experiences them. The closest land is the Mariana Islands, which have a small total population. The earthquakes happen far offshore, often miles below the seabed itself. The energy disperses through enormous volumes of rock and water. By the time it reaches a populated area, it has been damped to almost nothing. But the energy released is staggering. A single moderate earthquake at the trench can release more energy than a large nuclear weapon. The biggest events, the ones that historically have struck similar subduction zones around the Pacific, have released more energy than humans have ever produced from any source. The Pacific Plate moves at about the speed of growing fingernails, roughly 1.5 inches per year. That sounds slow. Multiply it by the area of the plate involved. Multiply that by the mass of rock being shifted. The forces are unimaginable. The trench itself is the visible result of this slow violence. Every inch of depth in that 7-mile drop was carved by the slow dragging of the Pacific Plate downward. Every ridge along the trench wall is a record of past slips. Every undersea volcano in the Mariana Arc is fed by water and minerals being squeezed out of the descending plate. The whole region is a living scar, constantly reopening, constantly remaking itself. Scientists monitor the trench using seafloor sensors. They place instruments at the bottom of the deep ocean that record vibrations continuously. The data flows back to research centers, where it is analyzed for patterns. The hope is to better understand what causes the largest earthquakes, and possibly to give some warning before the next one. The next big one is coming. The math demands it. The tectonic forces have not stopped. They will not stop. The only question is when, and how much energy will be released, and whether the resulting wave will reach a coastline where people live. And that wave, when it comes, has a name: tsunami. A tsunami is not just a big wave. It is a disturbance of the entire water column from the seabed to the surface. Most ordinary ocean waves are caused by wind. Wind only affects the top layer of water. A tsunami, by contrast, starts when the seabed itself moves. The whole column of water above it gets shoved at the same instant. The energy radiates outward in all directions. The most dangerous tsunamis in human history have come from subduction zone earthquakes. The 2004 Indian Ocean tsunami. The 2011 Tohoku tsunami in Japan. Both were triggered by subduction zone events in which a section of the seafloor suddenly jumped upward. The Tohoku quake moved a section of the Japanese seabed by tens of feet in a matter of seconds. The water above moved with it. The resulting wave killed nearly 20,000 people. The Mariana Trench is a subduction zone. It has the same fundamental geometry as the trenches that generated those disasters. It sits along the same ring of fire that has produced almost every major Pacific tsunami in recorded history. The question is not whether it can generate tsunamis. The question is how big and how often. Historical records of large tsunamis, specifically from the Mariana Trench, are surprisingly thin. The trench has produced fewer documented megathrust events in the modern era than some other Pacific subduction zones. Researchers debate why. Some believe the geometry of the Mariana subduction is unusual, with the Pacific Plate diving at a steeper angle than at most other trenches. The steeper angle may release stress in many smaller events rather than rare giant ones. Other researchers believe the trench is simply storing energy that has not yet been released, and that a major event is overdue. The lack of certainty is itself the problem. The trench is not well monitored. The waters around it are remote. Most of the seafloor sensors capable of recording precursor signals are concentrated near populated coastlines elsewhere in the Pacific. The Mariana region itself has a sparse network of instruments. If a magnitude 9 earthquake were to occur along the Mariana Trench tomorrow, the resulting tsunami would radiate outward across the Pacific. It would reach Guam and the northern Mariana Islands within minutes. It would reach Japan, the Philippines, and other parts of Southeast Asia within hours. It would eventually reach Hawaii and the west coast of North and South America. The amount of warning each location received would depend on how quickly the earthquake was detected and how fast the alert systems could relay the information. The closer to the trench, the less warning possible. The Mariana Islands themselves would have almost none. The wave height for the closest islands could exceed 30 feet, depending on the specific characteristics of the earthquake. Coastal cities like Guam's Tumen Bay, with its hotels and resorts crowded near the shore, would be in the direct path. Researchers continue to study the trench for signs that stress is building toward a major release. They look at small earthquake patterns. They measure changes in seafloor shape using satellite data. They monitor the slow movement of GPS markers on the islands. They have not yet identified clear precursor signals to the next big one. The science is still developing. What they have identified is that the trench is the deepest visible evidence of an enormous ongoing geological process that humans have very little ability to predict or control. The plate is going under. It will keep going under. The forces will continue to build. Sooner or later, the rock will slip. And the slip is connected geologically to one of the most fundamental forces shaping our planet: the slow eating of one continent by another. The Pacific Plate is the largest tectonic plate on Earth. It covers an area of more than 60 million square miles. It includes most of the Pacific Ocean basin and parts of several continents along its edges. It is also old. The western edge of the Pacific Plate, the part that touches the Mariana Trench, formed roughly 170 million years ago. The rock down there is some of the oldest oceanic crust on the planet. Old oceanic crust has a particular property. It is cold, and cold rock is dense. When the Pacific Plate meets the smaller Mariana Plate at the trench, the difference in density is what determines what happens next. The colder, denser Pacific Plate cannot float over the warmer, lighter Mariana Plate. It dives underneath instead. The geometry is forced by physics. The dense plate goes down. The lighter plate stays up. The trench is the surface expression of this enforced descent. What happens to the Pacific Plate after it dives is one of the more remarkable stories in geology. The plate does not simply disappear into the mantle. It carries with it a layer of ocean sediment. It carries seawater trapped in pores within the rock. It carries minerals that formed at the surface. As the plate descends deeper into the planet, it heats up. The minerals start to release water. The water rises into the rock above. The rock above, now wet, melts at lower temperatures than it would otherwise. The melted rock rises further, eventually reaching the surface as volcanic eruptions. This is why the Mariana Islands exist. They are a chain of volcanoes formed by the melting of rock above the descending Pacific Plate. The water released by the dying plate becomes the trigger for the volcanoes. Without the trench, the islands would not exist. The Mariana Plate would be a flat seabed instead of an arc of volcanic peaks. The plate keeps going down. Eventually, it reaches a depth of hundreds of miles within the mantle. There, it slowly mixes back into the rock of the planet. Seismic instruments around the world have actually traced the descending Pacific Plate using earthquake waves. The waves travel slightly differently through cold descending plate material than through surrounding mantle rock. By measuring the differences, geologists can essentially see the slab of ancient ocean floor still descending toward the core. This entire process is part of the great recycling system that keeps the surface of Earth dynamic. Without subduction, the planet would look more like Venus or Mars, static, geologically dead. Subduction is what keeps continents moving, what keeps mountains rising, what keeps volcanoes active, what generates the magnetic field that protects life from cosmic radiation. And it all happens, in this part of the world, right at the bottom of the Mariana Trench. The rate of subduction here is not constant. The Pacific Plate is moving northwest at about 1.5 inches per year on average, but the rate of consumption at the trench is closer to 2.5 inches per year because of the way the plates are shaped. This is the speed at which the trench is, in a real sense, swallowing the Pacific Ocean floor. Slowly, but unstoppably. Run the math out. Over 100 million years, that is hundreds of miles of crust pulled down into the mantle. Vast areas of ocean floor that once existed at the surface are now somewhere far below, slowly being recycled into new rock. The Pacific Plate, ancient and enormous, is being eaten alive at its western edge. And as the plate descends, water and chemicals cook out of it. Some of those chemicals end up in the volcanic islands above. Others escape much earlier, leaking back through the seafloor in places we are only beginning to understand. When most people think of underwater hydrothermal vents, they picture the famous black smokers, tall chimneys of mineral deposits towering above the seafloor, blasting out plumes of superheated dark water full of dissolved metals. Black smokers are dramatic. They are beautiful in their own way. They host strange ecosystems built around chemicals instead of sunlight. They have been featured in countless documentaries. Black smokers exist in many parts of the ocean. They are not the most unusual vents found near the Mariana Trench. The truly strange ones are different. They are pale instead of black. The water leaking from them is not boiling hot. The chemistry is not acidic. These vents do not look like the famous chimneys at all. They look like soft, ghostly mounds of pale stone, sometimes growing into spires that rise dozens of feet from the seabed. The water flowing through them is highly alkaline, almost the opposite of seawater chemistry, and only moderately warm compared to the true black smokers. These structures are called serpentinite chimneys, or alkaline vents. They form when seawater seeps deep into the seafloor through cracks created by the trench. The water reacts with rocks rich in iron and magnesium. The reaction transforms the rocks into a different mineral called serpentinite and releases hydrogen gas, methane, and other compounds. The transformed rock and the resulting fluids are then forced back up to the seafloor, where they emerge as pale, alkaline chimneys. The most famous example of this kind of vent system is not actually in the Mariana, but in the Atlantic Ocean, called Lost City. However, similar systems are now being discovered in the deep waters around the Mariana Arc. Some of them have been studied in detail. Others are barely known at all. What makes these vents so interesting is what lives in them. The water flowing through alkaline vent chimneys is rich in dissolved hydrogen. Hydrogen is an excellent source of chemical energy for certain kinds of microorganisms. These microorganisms do not need sunlight. They do not need oxygen. They live entirely on the chemistry of the vent fluids. They build colonies inside the porous structure of the chimneys themselves, where the warm alkaline fluid mixes with the cold seawater outside. The ecosystems that grow around these vents are unique. They include tube worms, specialized crabs, and a variety of microbial communities that survive in conditions found nowhere else on Earth. Some of the microbes use chemical reactions that have been preserved, almost unchanged, since long before complex life existed on the surface. The vents are also places of unusual mineral deposition. The interaction between the fluid chemistry and the surrounding seawater causes unusual minerals to precipitate out and accumulate. Some of the chimney structures grow remarkably fast for the deep ocean environment, adding inches per year. Others grow slowly over thousands of years, building enormous spires of pale stone that look almost cathedral-like in submersible footage. Scientists are particularly interested in alkaline vents because they may be among the closest analogs we have to the conditions in which life on Earth first formed. The combination of warm fluids, dissolved hydrogen, mineral surfaces, and isolated chambers in the chimney structure may have provided exactly the right environment for the assembly of the first cells. Research expeditions to these vents are difficult. The chimneys are fragile. They are easily damaged by submersibles or robotic arms. They are scattered across remote areas of seafloor that have never been mapped in detail. Finding new ones requires luck, patience, and the right combination of imaging tools. Each new vent discovered is a small revolution, new microbes, new chemistry, new clues about how life on this planet or any other can begin and survive in environments that look nothing like the surface world. And the microbes that live in these places, the ones that breathe sulfur and hydrogen instead of oxygen, are unlike anything we ever expected to find. If you grew up learning that life requires oxygen, the deep sea is going to break your understanding of biology. Vast communities of microorganisms thrive in the trench environment without using any oxygen at all. They use other chemicals instead. Some of them breathe sulfur. Some of them breathe iron. Some of them breathe minerals that you would not normally associate with biology. The technical term for this is chemosynthesis. It is the deep ocean equivalent of photosynthesis. Plants on the surface use sunlight to convert carbon dioxide and water into food. Microbes in the deep use chemical reactions to do the same thing, building organic molecules from inorganic raw materials, powered by chemistry instead of light. The microbes around the Mariana Trench are some of the most diverse chemosynthetic communities on the planet. They include archaea, a category of single-celled life that is biologically distinct from both bacteria and animals. Archaea are extremely ancient. Some scientists believe they are the closest living relatives to the very first cellular life on Earth. Some of the archaea found near the trench can survive at temperatures and pressures that would destroy almost any other organism. They can live in highly acidic water. They can live in highly alkaline water. They can live in fluids saturated with toxic metals. They can live with no oxygen, no sunlight, and only the slow chemistry of seeping mineral fluids to power their cells. The bacteria are equally remarkable. Some species can metabolize sulfur compounds, producing energy from chemical reactions that other life forms find poisonous. Others can break down hydrocarbons, including some of the methane that leaks naturally from the seabed. Some can fix nitrogen from dissolved gases in the water, providing the basic building blocks of life to the ecosystems around them. Even more astonishing, some of these microbes appear to be embedded inside solid rock. Researchers have collected samples of seafloor rock from around the Mariana Trench and found living microbes inside the pore spaces. The cells are surviving in tiny pockets of fluid trapped within the rock structure. They reproduce extraordinarily slowly. Some species may divide only once every several hundred years. They are essentially in suspended animation, sustaining themselves on the slow trickle of chemical energy that filters through the surrounding stone. The total mass of microbial life living within the deep ocean seafloor, including the rocks themselves, may be larger than all the animal life in the oceans combined. The number is hard to measure precisely. The rocks are difficult to sample. The cells are difficult to detect. But every new study suggests the deep biosphere is much more populous than anyone suspected even 20 years ago. This has profound implications for the search for life on other planets. If microbes can survive embedded inside rock, in cold and dark and crushing pressure, drinking the chemistry of mineral fluids, then similar life could potentially exist beneath the surfaces of icy moons in our own solar system. Europa, Enceladus, both are believed to have liquid water oceans beneath their frozen surfaces. If life can endure in the conditions of the deep Mariana, it might be able to endure in the conditions of those distant worlds. NASA missions designed to search for extraterrestrial life now use deep ocean microbial communities as a model for what they might find. The Mariana Trench is, in this sense, a laboratory for understanding the limits of life itself. Anywhere on this planet that life is found in extreme conditions becomes a clue about what life elsewhere might look like. The microbes do not announce themselves. They do not glow in the dark. They do not produce spectacular structures. They are quiet. They are patient. They have been doing what they do for billions of years, and in some cases, the work of studying them was hidden from the public for political reasons that are still not fully understood. During the height of the Cold War, the Mariana Trench attracted attention from more than just American researchers. Soviet scientists were also actively studying the deep Pacific. The Soviet Union maintained a substantial fleet of oceanographic research vessels throughout the 1960s and 70s. Many of those vessels operated in the Western Pacific, sometimes in the same waters as American teams. What exactly the Soviet researchers found during those decades is, in many cases, unclear. A significant portion of Soviet deep-sea research from that era has never been fully translated, declassified, or made available to the international scientific community. Some of the records were lost when the Soviet Union dissolved in 1991. Some were absorbed into the Russian Academy of Sciences and became difficult to access. Some appear to have been deliberately classified at the time and never released. The known parts of the Soviet program are impressive. Soviet research ships made repeated trips to the Mariana region. They lowered sensors. They took sediment samples. They mapped sections of the seafloor using their own sonar systems. Some of the Soviet bathymetric data was eventually shared with the international community and incorporated into world maps. Other parts have never appeared in any public data set. A few specific Soviet expeditions stand out in the historical record. One famous example involves a deep-diving submersible called Mir, developed in the 1980s by a Soviet engineering team. The Mir submersibles were rated to about 20,000 feet, which is impressive, but not enough to reach the bottom of the Challenger Deep. They were used extensively for deep-sea research, including some work in the Western Pacific. Whether earlier Soviet vessels attempted any deeper work that has not been publicly disclosed is a question that occasionally comes up in deep-sea history circles. There are also persistent rumors, never confirmed, about Soviet acoustic monitoring of the deep Pacific during the Cold War. The American SOSUS network had a Soviet equivalent. The Soviets reportedly placed their own listening devices at strategic points in the Pacific. What those devices recorded is not part of any public archive. If the Soviet hydrophones picked up sounds similar to the bloop or the biotwang, the recordings have never been released. This is the kind of gap in the historical record that makes deep-sea researchers uncomfortable. There may be valuable scientific data sitting in archives somewhere, untranslated and unstudied. There may be discoveries that were made and then lost when the political situation changed. The Mariana Trench is a global natural feature. The work done to understand it has been split between countries and political eras. The integration of all that work into a single, comprehensive picture has never really happened. A small effort in the late 1990s, after the Cold War ended, attempted to digitize and share Soviet-era oceanographic data. The project produced useful results in some areas, but the volume of historical data was enormous, and only a fraction of it was ever processed. Many of the original paper records are now in poor condition. Many of the scientists who originally collected the data have died. Institutional memory has faded. China has more recently become a major player in deep-sea research. The Chinese submersible Fenduji has made dozens of crewed dives to the Challenger Deep. Chinese teams have published a growing body of research about trench biology, geology, and chemistry. But Chinese deep-sea programs also operate with significant national security classification. Some of what Chinese expeditions have found has been published openly. Other portions of the work remain restricted. The result is that even today in 2026, the publicly available knowledge of the Mariana Trench is incomplete. Major countries have done major research. They have not all shared it. The map of the deep is patchy, not just because of what we have failed to discover, but because of what some of us have chosen not to reveal. And occasionally, those patchy maps reveal sonar returns that nobody can quite explain. Sonar works by sending a sound wave down through the water and listening for the echo. when it bounces back off something solid. The time it takes for the echo to return tells the operator how far away the object is. The shape and intensity of the echo can suggest, with the right interpretation, what kind of object produced it. Modern multi-beam sonar systems mounted on research vessels can scan a wide swath of seafloor at once. They send dozens of beams in a fan pattern across the area below the ship and build up a detailed image of the topography by combining all the returns. In the right conditions, multi-beam sonar can resolve features as small as a few feet across, even at depths of several miles. Sometimes in the deep waters of the Pacific Ocean near the Mariana Trench, sonar returns come back that surprise the operators. The most common surprise is what oceanographers call the deep scattering layer. It is a thick, moving mass that shows up on sonar as a fuzzy band across the screen. For decades after sonar was first used in the open ocean, scientists were baffled by it. The layer would appear during the day at one depth, then rise toward the surface at night, then sink back down before dawn. It was not a real object. It was something biological. Eventually, researchers figured out that the deep scattering layer is composed of countless small marine animals migrating up and down the water column every day. Tiny fish, squid, krill, plankton. They all rise toward the surface at night to feed in the upper waters, where there is more food, and sink back down during the day to hide from predators in the dark. The total mass of the deep scattering layer is enormous. It represents the largest daily migration of biomass on the planet. That is the explained kind of surprise. The unexplained kind is rarer and less discussed. Occasionally, sonar operators near deep trenches report returns from objects that do not behave like the deep scattering layer, do not match any known geological feature, and do not correspond to anything visible on the surface. The objects appear briefly, return strong echoes, and then disappear. Sometimes they move. Sometimes they hold position for minutes before vanishing. Most of these returns can probably be explained by individual large animals. Whales, schools of tuna, squid concentrations. The deep ocean is full of life that occasionally shows up as a strong sonar return without being seen on the surface. Most operators simply log the contact, file it away, and move on. But some returns are more puzzling. The operators report objects much larger than any known animal. Objects with shapes that suggest something solid rather than living. Objects in places where the depth and pressure should preclude any conventional explanation. How much of this is real, and how much is the natural noise of working with imperfect equipment in a vast and unknown environment is hard to say. Sonar in deep water is not a perfect tool. False returns are common. Equipment glitches happen. Unusual reflections from underwater layers of different temperature or salinity can produce ghost signals that look solid, but are not. Most experienced operators are appropriately skeptical. They have seen too many strange returns turn out to be ordinary explanations. Most are not eager to make claims about anomalies that cannot be verified. But there are enough unexplained sonar reports from the deep Pacific to fill a small archive. They sit in the records of various research institutions and naval departments around the world. Most of them will probably never be revisited. The cost of going back to investigate a single anomalous sonar return is enormous. The likelihood that the cause has long since moved on or disappeared is high, so they sit. Notes on screens, echoes from things that may or may not have been there. Pieces of a puzzle no single person has the access or the resources to assemble. And there is a related kind of mystery. Places in the deep where even the satellites that map our planet from above cannot reliably read the depth. Most of what we think we know about the world ocean floor comes from a single technique: satellite altimetry. Satellites in orbit measure the height of the ocean surface with extraordinary precision. The surface of the ocean is not perfectly flat. It is shaped by gravity. A massive underwater mountain pulls water toward it slightly, creating a tiny bump on the surface above. A deep underwater trench has less gravitational pull, creating a tiny depression. By measuring the bumps and depressions of the ocean surface, satellites can infer the rough shape of the seafloor below. Satellite altimetry has produced low-resolution maps of essentially the entire world ocean. It is the reason that the basic outlines of the major trenches and seamounts are known. Without it, the ocean floor would be almost completely uncharted. The technique has limits. Satellite altimetry can only resolve features larger than about a mile across. Anything smaller is invisible. The deep details of trenches, the smaller seamounts, the canyons, within canyons, all of those features require direct sonar measurement from a ship. There is another limit that gets less attention. Some areas of the ocean produce satellite altimetry signals that are weak or distorted. The shape of the surface in those regions does not respond cleanly to the gravity of the seafloor below. The reasons are complex and still being studied. Local variations in temperature, salinity, currents, and atmospheric pressure can all affect the surface in ways that interfere with the altimetry signal. Researchers have informally called these regions shadow zones, areas where the standard mapping technique does not give clear results. Some shadow zones exist near the deepest trenches, including parts of the Mariana region. The water surface above the trench does respond to the deep gravity of the seafloor, but other factors muddy the signal. The result is that the satellite-derived maps of the trench area are less reliable than they appear. Direct sonar mapping from research vessels can fill in the gaps, but as we have already discussed, the trench is enormous, and the mapping budget is limited. Large stretches of the deep Pacific remain in a state where the satellite data is uncertain, and the direct sonar data is missing entirely. The implications are subtle, but real. When you look at a published map of the Mariana Trench, you are looking at a composite. Some of it is detailed sonar data from specific surveys. Some of it is satellite altimetry. Some of it is interpolated. The boundaries between these different data sources are not always marked clearly. A casual viewer might assume the entire trench has been mapped uniformly. It has not. This matters for several reasons. If you are searching for a lost vessel, the available map may not be accurate enough to plan a search pattern. If you are tracking long-term changes in the trench shape, the noise in the data may hide real geological changes. If you are looking for unusual features, like the alkaline vents we discussed earlier, the maps may not be detailed enough to tell you where to look. The shadow zones are also interesting in their own right. They represent places where standard remote sensing methods lose their grip. They are reminders that even our most sophisticated tools have blind spots. The deep ocean is not a single problem to be solved with one technology. It is many problems requiring many different approaches. Mapping the trench is not just a matter of more ships. It is a matter of better integration of every kind of data we can gather. Sonar from vessels, satellite altimetry from orbit, bathymetry from autonomous gliders, seismic data from seafloor sensors. Each method has strengths, each has weaknesses. Combining them is hard. Even the planet next door is easier to chart in some ways than the bottom of our own ocean. Here is one of the most uncomfortable facts in modern science. We have higher resolution maps of the surface of Mars than we have of the floor of our own ocean. The same is true for the Moon. The same is even true for several other planets and large moons in our solar system. How is that possible? Mars is mapped by orbiting spacecraft equipped with cameras and laser altimeters. The Mars Reconnaissance Orbiter has been circling the planet since 2006. It carries an instrument called HiRISE, which can resolve features on the Martian surface as small as about 3 feet across the entire planet. We have detailed pictures of vast stretches of Mars that show individual rocks, small craters, dune patterns, and surface textures in remarkable detail. The Moon has been mapped by the Lunar Reconnaissance Orbiter, which has produced topography measurements with vertical accuracy of about a foot. We know the shape of the lunar surface to that level of precision across essentially the entire body. Every crater, every ridge, every flat plane. The ocean floor of Earth, by contrast, is mapped at high resolution across only about 25% of its area. The remaining 75% is known only at low resolution, at best. vast stretches of the deep ocean have never been scanned by anything more accurate than satellite altimetry, which, as we just discussed, has its own limitations. Why the difference? The answer is water. Light, radio waves, and laser beams all penetrate water poorly. The techniques that work so beautifully for mapping airless surfaces from orbit do not work at all for mapping a surface covered by miles of liquid. Sound waves work in water, but they require a vehicle in the water itself to send and receive them. Every square mile of high-resolution ocean floor mapping requires a research vessel to physically sail over that mile, often multiple times. The vessels are expensive, the ships are slow, the available time is limited. Compare the budgets. The total amount spent on space exploration globally over the past 50 years has been many tens of billions of dollars. The total amount spent on deep sea mapping has been a small fraction of that. We have, as a civilization, made a choice to look outward more than we have looked downward. There's also a perception problem. Space is exciting. Other planets feel like the future. The deep ocean is on Earth. It is not, in the popular imagination, a frontier in the same way. The funding follows the imagination. The Seabed 2030 project is trying to change this. The goal is to map the entire ocean floor at modern resolution by the end of the decade. As of recent updates, the project has reached about 26% of its target. That is real progress from the 6% it started with in 2017, but it is also far short of complete. Even if the project succeeds, the maps it produces will be coarser than the maps we already have of Mars. Seabed 2030 aims to resolve features about 300 to 400 feet across. That is impressive for an ocean. It is also much less detailed than what HiRISE shows on Mars. The deep ocean will remain, in real terms, less explored than the surface of another planet, even after the project is finished. There are people who find this fact unsettling. The deep ocean is part of our own planet. It influences our climate, our weather, our food supply, our coastal safety. Knowing it well should be a higher priority than it is. But the funding, the political attention, and the cultural imagination remain elsewhere. The Mariana Trench, in particular, sits inside the largest unmapped frontier on Earth. We know its general outline. We know its depth, approximately. We do not know in detail what waits at the bottom across most of its hundreds of miles of seafloor. And one of the reasons we have been hesitant to map it more thoroughly is that, decades ago, certain governments wanted to use it as a convenient place to dump some very dangerous garbage. In the 1970s and early 1980s, the world was running out of places to put its nuclear waste. The amount of radioactive material being produced by power plants, military facilities, and medical institutions was growing fast. The places to safely store it were not. Underground repositories were politically controversial. Surface storage was visibly dangerous. The waste kept piling up. Some governments and scientific advisors began to look seriously at the deep ocean as a disposal site. The proposals took several forms. The simplest involved sealing nuclear waste in heavy containers and dropping them into the deepest parts of the ocean, where they would, in theory, be too far down for any human to retrieve and too far from the surface for any contamination to reach the biosphere. A more elaborate version involved placing the containers at the bottom of subduction zone trenches, including the Mariana Trench, where the descending tectonic plate would, over millions of years, carry the waste down into the molten layer of the planet. The subduction disposal idea was particularly attractive on paper. The trench was deep. The plate was descending. Anything dropped in would, in geological time, be swallowed by the Earth itself. No human would ever see it again. The waste would mix with the mantle, where it would be diluted to insignificance over hundreds of millions of years. Japan proposed a version of this in 1979, considering disposal of low-level nuclear waste in deep waters near the Northern Mariana Islands. Other countries, including the United Kingdom, the United States, and the Soviet Union, conducted feasibility studies of various deep ocean disposal options during the same era. The plans never moved beyond the proposal stage at the major scale. International agreements eventually banned the deliberate disposal of nuclear waste in the ocean. The London Convention, signed initially in 1972 and progressively strengthened, made it illegal to dump high-level radioactive material at sea. A later amendment in 1993 extended the ban to all radioactive waste. Why did the plans fail? Several reasons. The first was scientific uncertainty. The exact behavior of subducting plates is not as predictable as the early proposals assumed. The plate does not necessarily carry everything dropped onto it cleanly down into the mantle. Some material can be scraped off and accumulated in the trench, rather than descending. Some can leak back into the water column over long timescales. The original promise of permanent disposal was always more theoretical than guaranteed. The second was political. As public awareness of environmental issues grew through the 1970s and 80s, the idea of deliberately dumping nuclear waste anywhere in the ocean became increasingly unpopular. No government wanted to be the one defending such a plan in front of an angry international audience. The third was earthquake risk. Subduction zones are seismically active. The trench is one of the most earthquake-prone places on Earth. Dropping nuclear waste containers into a region of constant seismic activity raised the possibility of containers being damaged, opened, or moved unpredictably by future earthquakes. The supposed safety of deep ocean disposal looked weaker the more carefully it was examined. But here is the thing about banning a practice. It does not necessarily mean the practice never happened, only that it is now illegal. Records from the 1960s and 70s, from various countries, contain hints of unauthorized disposal events that were never fully investigated. Some Soviet nuclear waste was almost certainly dumped in Arctic waters during the Cold War. Some Western nuclear waste was disposed of in the Atlantic in ways that were later judged improper. Whether anything was ever actually placed in the Mariana Trench is officially unknown. The records of who was operating in the Western Pacific during certain decades are incomplete. The water is too deep for routine inspection. If something was put down there decades ago, it might still be there now, slowly corroding, in a place no human has the means to easily reach or recover. We may never know. What we do know is that diving into the trench, even today, is not safe. And one recent disaster has reminded everyone just how unforgiving the deep ocean can be. In June 2023, a small submersible called Titan disappeared during a dive to the wreck of the Titanic in the North Atlantic. The Titanic sits at a depth of about 12,500 feet. That is deep, but it is less than half the depth of the Challenger Deep. By the standards of extreme deep-sea exploration, the Titanic is not in the abyss. It is in the upper part of the deep ocean. The Titan was operated by a private company called OceanGate. It carried 5 people: the pilot, a billionaire passenger, an explorer, a businessman, and his teenage son. They had paid for the trip. The submersible was designed and built using methods that some experts in the deep submersible community had warned were unsafe. Communication with the surface was lost about an hour and 45 minutes into the dive. A massive search began immediately. Ships and aircraft from multiple countries converged on the area. For 4 days, the world held its breath. There was hope, briefly, that the submersible might be intact on the seafloor with its occupants still alive. Then a remotely operated vehicle found debris on the bottom of the Atlantic, near the Titanic wreck. The Titan had imploded. The 5 people inside had died in less time than it takes a human nerve to register pain. The implosion was so fast and the pressure so absolute that the vessel and its occupants were destroyed in the blink of an eye. Acoustic monitoring equipment, including United States Navy systems, had actually detected the implosion at the time it happened. The sound was unmistakable to people who knew what to listen for. The Navy did not announce the detection until days later, after the search had turned up the debris. The Titan disaster sent shockwaves through the deep submersible community. It also forced a public reckoning with the realities of extreme depth diving. Many of the warnings that experienced engineers had made about the Titan's design were vindicated, tragically and in public. Several of those engineers had publicly said, before the disaster, that the submersible was not safe enough for the depths it was attempting. The lessons applied immediately to the much harder problem of diving in the Mariana Trench. The pressure that destroyed the Titan at 12,500 feet is roughly a third of the pressure at the bottom of the Challenger Deep. Any submersible attempting to reach the deepest point on Earth has to be designed and tested with even more rigor than the Titan apparently was. Most of the deep submersibles currently rated for the Challenger Deep have been built by experienced teams with extensive testing programs. The DSV limiting factor, built by Triton Submarines for Victor Vescovo's 5 Deeps expedition, is one example. The Chinese Fendoji is another. Both have extensive operational records and have been subjected to detailed engineering analysis. Both have made multiple successful dives to the bottom of the trench and returned safely. But the Titan disaster has also affected funding and public perception. Insurance for deep submersible operations has become more expensive. Regulatory scrutiny has increased. Some adventure tourism programs that had been considering offering deep ocean dives have backed away from those plans. The era of casual deep tourism, which was just beginning before the Titan, has been delayed. This is probably for the best. The deep ocean does not care about your enthusiasm. It does not care about your insurance. It does not care about your engineering optimism. It applies pressure with absolute uniformity, and any flaw in your equipment becomes the reason you do not come home. The Titan story is a reminder, a vivid one. The deep is dangerous. Even the famous wreck of the Titanic, which sits in the upper deep, is a hostile place that can kill in an instant. The trench is dramatically harder. The trench is dramatically less forgiving. And the trench is not just one deep place. There are at least 2 within the Mariana system, and the second one is barely studied at all. When most people talk about the deepest place on Earth, they mean the Challenger Deep. That is the famous one. The one Trieste descended into. The one Cameron filmed. The one Vescovo has visited multiple times. But the Mariana Trench has a second deep basin that is almost as famous in the scientific community and almost completely unknown to the general public. It is called the Sirena Deep. The Sirena Deep lies about 150 miles east of the Challenger Deep, along the same trench system. It is the second deepest known point in the ocean. Its maximum depth is approximately 35,460 feet, only a few hundred feet shallower than the Challenger. By any normal measure, it is a place of extraordinary depth, pressure, and isolation. The Sirena Deep was discovered in 1997, the same year as the bloop. Its existence had been suspected for some time, but the precise depth measurement that confirmed it as the second deepest point came from a survey that year. The name Sirena comes from the mermaid figure, fitting for a deep ocean basin that has spent most of its history hidden from human view. Despite being one of the deepest places on Earth, the Sirena Deep has been visited by humans only a handful of times. Crude dives to it can be counted on a single hand. There is a place in the Western Pacific where the ocean floor splits open and falls away into nothing. It is shaped like a long crescent scar, almost 1,600 miles from end to end, curving east of the Mariana Islands. Sailors above it see only blue water. They do not see what is underneath them. The Mariana Trench drops nearly 7 miles straight down. To picture that, imagine standing on the deck of a ship. Below your feet, the water keeps going for the same distance you would drive on a long highway commute to work. No light, no warmth. No sound from the world above ever reaches the bottom. The deepest spot has a name, the Challenger Deep. Around 36,000 feet down. If you took Mount Everest, the tallest mountain on the planet, and dropped it into this trench upside down, the peak would still sit more than a mile below the surface of the sea. The whole mountain, swallowed, with room to spare. Most of the ocean has an average depth of about 2.5 miles. That alone is dark and cold and almost unreachable. But the Mariana Trench is nearly 3 times deeper than that. It is a separate world. Scientists call it the Hadal Zone. The name comes from Hades, the underworld. They had to invent a new word because no other place on Earth behaves like it. The pressure down there is unlike anything you have ever experienced. At the bottom, every square inch of surface gets crushed by more than 15,000 pounds of force. That is the weight of 50 fully loaded jumbo jets stacked on top of you. A foam coffee cup sent down on the outside of a submersible comes back the size of a thimble. Solid metal flexes. Glass shatters from the inside out. And yet, something lives down there. Things move through that pressure as if it were nothing. Soft, pale, almost glowing. We will get to those creatures soon. But first, the geography itself. The trench is not just a hole. It is a tear in the crust of the planet, formed where 2 enormous plates of rock collide. One plate is being shoved underneath the other, dragged down into the molten layer below. This grinding, slow-motion violence has been happening for tens of millions of years. The trench is the open wound where it happens. That movement is what makes the location so unstable. Earthquakes hammer the seafloor on a regular basis. Some of them release more energy than a city-sized nuclear blast. People on land never feel them. The water absorbs the shock. But sensors on the deep floor record the screaming of rock against rock. There are 3 deep basins inside the trench. 3 separate pockets, each plunging past the 7-mile mark. The central one is Challenger Deep. There is also the Serena Deep to the east, and a third western basin barely studied at all. Each one could hide entire ecosystems we have never witnessed. Each one could hide objects that fell from above and were never recovered. Ships pass over this place every single day. Cargo vessels, cruise liners, naval patrols. None of them have any idea what is directly underneath their hull. And the strangest part is that the people best equipped to look down there have chosen not to. The United States Navy owns some of the most advanced sonar equipment ever built. They can track a foreign submarine moving silently across an entire ocean basin. They can pick up a whale's heartbeat from miles away. If anyone on Earth could fully map the Mariana Trench in high resolution, it would be them. So here is the strange part. They have not. As of right now, less than a quarter of the world ocean floor has been mapped at modern resolution. For the deepest trenches, the number is even smaller. Most of the Mariana Trench has been scanned only in rough outline. Wide sweeps of low-resolution sonar that show the general shape, but miss anything smaller than a city block. Entire valleys, ridges, and overhangs sit there unrecorded. A sunken vessel the size of a school bus could be down there right now and nobody would know. The official reason is simple: cost, time, difficulty. Mapping a single square mile of deep trench at high resolution can take a research ship a full day of sailing back and forth in straight lines. Crews call it mowing the lawn. The trench is over 100,000 square miles in area. Doing it all in detail would take decades and billions of dollars. That is the public answer. There is also a quieter one. The Navy classifies large amounts of its bathymetric data. Bathymetry is just a fancy word for the depth and shape of the seafloor. When a Navy ship sails over a deep trench with its full sonar suite running, the resulting map is not always shared. Some of it is locked away as a matter of national security. Submarine routes, listening posts, and the topography that hides them are considered strategic information. If a foreign power knew exactly where the deepest hiding places were, it would change the balance of power under the sea. So a portion of what the United States actually knows about the Mariana Trench, the rest of the world will never see. How much remains secret is itself a secret. The international project trying to fix the gap is called Seabed 2030. The goal was simple: map the entire ocean floor by the year 2030. When the project began in 2017, only 6% of the world ocean had been mapped to modern standards. By 2024, That number had climbed to about 26%. Real progress, but still nowhere near complete. And the deepest, hardest places are exactly the ones still missing. Here is something that should make you uncomfortable. We have higher resolution maps of the surface of Mars than we have of the floor of our own ocean. We have walked on the moon. We have landed robots on a comet flying through space. We still cannot tell you what the bottom of the Mariana Trench actually looks like in detail. Think about what that means. Right now, if a submarine vanished into the deeper basins of the trench, search teams would not even have a reliable map to look at. They would be hunting blind in a place where the pressure crushes their equipment within minutes. And blind hunting in the Mariana Trench is exactly what happened in the 1950s, when the Navy turned on a microphone network designed to listen for enemy ships. What it picked up instead was something nobody had ever heard before. In the 1950s, the Cold War was at its peak, and the United States Navy was terrified of one specific thing: Soviet submarines slipping silently across the Pacific without being detected. So the Navy did something enormous and almost completely secret. They strung gigantic underwater microphones across the ocean floor, hundreds of them, connected by armored cables to listening stations on shore. The system was called SOSUS, Sound Surveillance System. It worked because of a strange property of deep ocean water. Sound travels for thousands of miles down there with almost no loss of strength. A propeller turning in the Sea of Japan can be heard clearly by a hydrophone off the coast of California. The ocean is a giant whispering gallery, and the Navy had wired it for sound. For decades, every recording was classified. Operators in shore stations sat in dim rooms, headphones on, listening for the slow churn of Soviet engines. They learned to recognize every type of vessel by its acoustic signature: American submarines, Russian submarines, whales, earthquakes, volcanic vents. But every so often, the headphones picked up something nobody had ever cataloged. A growl that lasted for minutes and seemed to move across thousands of miles of ocean. A rising whistle that climbed in pitch with no obvious source. A rhythmic pulse that repeated for hours and then stopped without warning. The operators would write down the sound, mark the location, and pass the recording up the chain. Most of the time, the answer that came back was the same: unknown. When the Cold War ended, parts of the SOSUS network were quietly handed over to civilian science. The National Oceanic and Atmospheric Administration, known as NOAA, took control of some of the listening stations. For the first time, ocean researchers had access to one of the most powerful eavesdropping tools ever built. And the moment they started reviewing the recordings, they realized the Navy had been collecting something extraordinary. Tucked inside thousands of hours of audio were sounds that could not be matched to any known animal, ship, or geological process. Some of them were louder than the call of any creature in the ocean. Some lasted longer than any whale could possibly hold a single note. Some came from regions of the Pacific where almost no one had ever sailed, including the deep waters near the Mariana Trench. NOAA gave the strangest of these sounds nicknames: bloop, Julia, slow down, upsweep, biotwang. Each one a few seconds or minutes of recording that defied explanation. Each one a question scientists could not answer. The recordings were released to the public starting in the late 1990s. People listened to them on early internet forums and felt something between fear and wonder. The sounds were not pleasant. They were low and groaning and strangely organic. They felt alive. Researchers tried every theory they could think of: earthquakes, underwater landslides, submarines, whales. Some of the sounds were eventually pinned down. Slowed down was probably an iceberg dragging across the seafloor. Upsweep was traced to a cluster of underwater volcanoes. But others stayed mysterious for years. Decades, in some cases. And one of them, the loudest of them all, the one that sounded like something enormous calling out from the deep, kept its name and its mystery for almost 20 years. It was the loudest sound ever recorded by NOAA in open water. and nobody could agree on what made it. That sound had a name, the bloop, and what scientists eventually decided about it has not satisfied everyone. The summer of 1997 was when it happened. Two hydrophone stations more than 3,000 miles apart, both run by NOAA in the South Pacific, picked up the same noise at almost the same instant. It rose from below. It lasted about a minute. It was so powerful that it overloaded the recording equipment. They named it the bloop because that is what it sounded like when sped up. A deep, rolling, almost cartoonish gulp from the bottom of the world. Played at its actual speed, it was lower and longer, a kind of slow, grinding moan that seemed to swell out of the dark. What stunned the scientists was not just the sound itself. It was the volume. The bloop was louder than any blue whale, louder than any cargo ship, louder than any creature ever recorded in the history of marine biology. For something to be heard clearly across 3,000 miles of ocean, it had to be unimaginably powerful. If it was an animal, it would have to be many times the size of any whale that has ever existed. The internet, in its early years, ran wild with the recording. Theories piled up faster than anyone could test them. A giant unknown sea creature, a surviving prehistoric monster, a leftover dinosaur from before the asteroid. People listened to the bloop late at night with their headphones on and felt the hair on their arms stand up. NOAA, to their credit, kept investigating. For years, they had no good answer. The location of the source was somewhere in the southern Pacific Ocean, hundreds of miles off the coast of South America, far from any known shipping lane and far from any known whale population. Eventually, a theory took shape. The agency announced that the bloop most likely came from an ice quake, a giant block of ice cracking off an Antarctic glacier. They pointed to recordings of similar sounds taken from known iceberg events. Same low frequency, same slow rumble, same pattern of rise and fall. For most scientists, that was the end of it. Case closed. The bloop was ice. For a lot of other people, it was not the end of it at all. The reason is simple. The bloop was recorded in 1997. The closest point of Antarctic ice that could have made that sound was over 1,000 miles from the recorded location. Sound does travel that far in the ocean, but the bloop's signature did not perfectly match the icequake recordings NOAA used for comparison. It was close. It was reasonable, but it was not identical. There were also no satellite confirmations of a major calving event in that part of Antarctica during that week. No big iceberg appeared in the days afterward. The ice theory works on paper. The exact source iceberg has never been found and named, so the official explanation is icequake. The honest explanation is best guess. The bloop is filed away as solved, but the file has a soft edge. What that episode showed scientists was something deeper. The deep ocean is full of sounds that do not fit any known category. Most of them eventually find an explanation. Some of them resist for years. And some of them, like the one that came next out of the Mariana Trench itself, sound less like nature and more like a machine. A metallic ringing, a pulse from the deep. And it took 10 years to figure out what was making it. In 2014, NOAA was running a new kind of ocean survey. Instead of large research ships, they were sending small autonomous gliders, torpedo-shaped robots that drift slowly through the water, recording sounds, sending data back when they surface. Cheaper than a ship, quieter than a ship, capable of staying in the field for months. One of these gliders was working near the Mariana Trench, just east of the Mariana Islands, drifting through the dark above the deepest place on Earth. And somewhere in the recordings, scientists found a sound that stopped them cold. It lasted about 3 seconds. The first part was a low, grumbling moan, the kind of sound a very large animal might make. The second part was completely different. A sharp, high-pitched, metallic ring, like a struck piece of steel, like the ping a sonar makes in an old submarine movie. One co-author of the eventual study said it reminded her of the bridge alert from the original Star Trek. The team named it the biotwang. For a while, nobody had any idea what it was. The combination of organic groan and mechanical ping was almost impossible to match to a known animal. Whales make many sounds, but nothing in the cataloged libraries lined up with the second half of the biotwang. The metallic part felt wrong. It sounded built, not born. The first guess was a ship of some kind, maybe distant Navy sonar bouncing through the trench. But the timing and pattern did not match any known vessel activity. The second guess was a new species of beaked whale. Some beaked whales make unusual mechanical clicks, but none of them had been recorded near the Mariana region in those numbers. Years passed. The biotwang kept showing up in recordings. Always near the trench, always the same two-part structure. The grumble, then the ring. Scientists could measure it, count it, even map where it appeared most often in the ocean. They just could not say what was making it. Then, in 2018, a survey crew went out specifically to look for the source. They sailed the waters where the biotwang appeared most often, watching the surface, listening below. And they got lucky. They spotted 10 bride's whales swimming through the area. Bride's whales are large baleen whales, sleek and dark, not particularly well studied compared to their famous cousins. Of those 10 whales, 9 were recorded making the biotwang as they swam. The lead researcher said it perfectly. Once is a coincidence, twice is happenstance. 9 times is a bride's whale. To be sure, the team used artificial intelligence to comb through more than 200,000 hours of underwater recordings. The AI flagged every biotwang it could find. The patterns matched the migration of bride's whales across the western Pacific. So the biotwang got an answer. After 10 years. It was a whale, calling out across the deep, possibly using the trench itself as a kind of natural amplifier. But here is what stuck with researchers afterward. For a full decade, one of the most advanced ocean monitoring systems in the world had been recording a sound that experts could not identify. A common, large, perfectly real animal was making it. Right there, in open ocean, and nobody knew. If a bride's whale could go that long unidentified, what else is calling out down there that nobody has connected to a source yet? Because the biotwang is only one of the puzzles. NOAEA is still working through. There are others, and some of them have lasted even longer. The biotwang took 10 years to solve. The bloop took about 5 before NOAA announced its best guess. But there are other sounds in the NOAA archive that are still waiting for a final answer. Each one has a name. Each one has a story. Each one has a wave of scientists who have spent careers arguing about what made it. The first is called Slow Down. It was recorded in 1997, the same year as the bloop. It is a long, low, slowly descending tone that lasts around 7 minutes. 7 full minutes of one continuous sound, gradually dropping in pitch the way a record player slows down when you pull the plug. That is where the name came from. Slow Down was picked up off the coast of South America. The leading theory now is that it was caused by the slow grinding of an Antarctic iceberg dragging across the seafloor. Friction between ice and rock can produce long, descending tones as the speed of the slide changes. It is a clean explanation. It fits the physics. But the source iceberg has never been positively identified, and the same sound has been heard several times since from different locations. Some researchers think there is more than one explanation hiding inside the same nickname. Then there is Julia, recorded in 1999. About 15 seconds of moaning, rising and falling, almost like the voice of a person calling out from very far away. It was loud enough to be picked up across the entire Eastern Pacific listening array. The current best guess is that it came from a large iceberg running aground on the Antarctic seabed. But again, no specific iceberg has ever been matched to the recording. Upsweep came earlier. NOAA started picking it up in 1991. It is a long series of sweeping tones that climb upward in pitch, repeating over and over. Researchers eventually traced it to a region of underwater volcanic activity in the southern Pacific. The current theory is that lava meeting cold seawater creates pressure waves that produce the repeating upward whoop. That theory is mostly accepted now, but upsweep has been getting quieter over the years, and nobody is sure why. There is one more worth mentioning. It was called The Train, recorded in 1997. A long mechanical rhythmic clatter that genuinely did sound like a freight train rolling across a steel bridge. The source was traced to the Ross Sea, near Antarctica. The current explanation is, again, ice. Specifically, a giant iceberg dragging in a particular pattern across the seabed. You may notice a theme. Almost every long unexplained sound in the NOAA archive eventually gets attributed, with varying levels of confidence, to ice or volcanism. That is because those are the only natural sources powerful enough to be heard across thousands of miles of ocean. Whales are loud, but they cannot match a calving glacier or an erupting seamount. Here is the thing that bothers some researchers. The explanations are plausible, they are physically reasonable, but many of them remain hypotheses, not confirmed matches. Nobody has ever stood beside the iceberg in question and recorded it making the exact sound. Nobody has filmed the volcanic vent producing the exact upward sweep. The cases are closed in the public mind. In the scientific literature, they are often still listed as probable, and the deep ocean keeps generating new sounds. Every year, new recordings come in from autonomous gliders and seafloor sensors. Most are quickly identified. Some are added to the unsolved file. Listening to the deep is one mystery. Going down there in person is another, and what you have to survive to make that journey is almost unbelievable. You already know the pressure at the bottom of the Mariana Trench is enormous. Now picture what that actually means for an object trying to survive down there. Air pressure at sea level is what you feel right now. Your body is built for it. Every square inch of your skin is being pushed on by about 15 pounds of force from the atmosphere. You do not notice because the pressure inside your body matches the pressure outside. Equal forces. No squeeze. Now go underwater. For every 33 feet you descend, the pressure on you increases by another 15 pounds per square inch. Scuba divers feel this in their ears within seconds. By the time you reach a depth of about 300 feet, you are dealing with pressure 10 times stronger than what you grew up with. This is already the limit for most recreational diving. At 1 mile down, the pressure is about 230 times what you feel on the surface. At 2 miles down, it is over 460. The crushing force keeps building, mile after mile, with no break in the math. At the bottom of the Challenger Deep, almost 7 miles down, the pressure reaches more than 15,000 pounds per square inch. To put that in human terms, every fingernail-sized patch of your body would be holding up the weight of a small car. Every inch. Across your entire surface area. All at once. A solid steel sphere can survive that environment, but only if the steel is many inches thick and shaped perfectly. Even a tiny flaw in the metal becomes a fatal weakness. The pressure does not push gradually. It pushes everywhere at once with absolute uniformity. If the structure has any weakness, the failure happens in a fraction of a second. This is what implosion means. The water does not slowly leak in. The walls of the vessel collapse inward at thousands of miles per hour. Anything inside is compressed to a fraction of its size faster than human nerves can react. There is no pain. There is no awareness. There is just before and after. Engineers test deep submersible parts in pressure chambers on the surface. They take a piece of foam, or a coffee cup, or a styrofoam head, and send it down on the outside of a research vessel. When the equipment comes back up, the foam is the size of a thimble. The cup is a thumb-sized lump. The styrofoam head looks like a shrunken souvenir from a horror movie. Same shape. Tiny. That is what happens to anything compressible at full trench depth. Air pockets disappear. Soft materials harden. Even some metals, if they contain any internal voids, can crack from the inside out. Living creatures down there have solved this problem in a remarkable way. They do not fight the pressure. They equalize with it. Their bodies contain almost no air. Their cells are filled with fluids and proteins shaped to function under crushing force. Take one of these animals up to the surface, and it dies almost immediately, often before reaching the deck of the ship. The lack of pressure tears them apart from the inside. Down there, the pressure is the rule. Up here, it would be the killer. This is why every mission into the trench is a battle of engineering against physics. One small mistake in the design of a hull or a viewport, one hidden flaw in the steel, and the vessel becomes a tomb. The ocean does not give second chances at 15,000 pounds per square inch. And that is exactly what nearly happened on the very first crewed descent to the Challenger Deep. The hull cracked. The crew heard it. Military submarines are some of the most pressure-resistant vehicles ever built. Their hulls are thick, double-walled, and shaped to spread force across as much surface area as possible. They are designed to disappear into the ocean and operate quietly for months at a time. They are the apex predators of the underwater world, and almost none of them can go anywhere near the Mariana Trench. A modern attack submarine is rated to dive somewhere between 1,000 and 2,000 feet below the surface. The exact number is classified, but the public ceiling for most fleet submarines is well under a half mile. Beyond that depth, the vessel risks what the Navy calls catastrophic structural failure. Politely worded, deadly to the crew. The Mariana Trench is roughly 35 times deeper than the safe operating range of a top-of-the-line military submarine. It is not even close. A submarine that wandered into the wrong part of the Western Pacific and somehow drifted down into the trench would be crushed long before reaching the halfway mark. The reason is simple. Military submarines are built for speed, stealth, and weapons capacity. A pressure-resistant hull that can survive 7 miles down would be too heavy and too thick to be useful as a warship. It would be slow. It would carry less fuel and fewer weapons. It would be a giant steel ball, not a fighter. So the Navy makes a trade-off. Operational submarines stay shallow enough to fight. Specialized research submersibles do the deep work. And the gap between those two worlds is enormous. Even research submersibles, the small craft built specifically for extreme depth, struggle. The famous Alvin submersible operated by Woods Hole Oceanographic Institution has a maximum dive depth of about 14,000 feet. That is impressive. It is also less than half the depth of the Challenger Deep. Most of the world's deepwater research vehicles cannot reach the bottom of the trench. They are not built for that pressure. To go all the way down, you need a vessel built for one purpose only: surviving the absolute extreme. There have only been a handful of such vehicles in human history. Trieste in 1960, Deep Sea Challenger in 2012, DSV Limiting Factor beginning in 2019. A few others. Each one cost a fortune to design. Each one represented years of engineering work. Each one was, in essence, a tiny pressure vessel barely larger than a closet, surrounded by buoyancy material, dropped through the dark like a stone. Now imagine what happens if any of these vessels has even a small flaw. The story of the Titan submersible, which imploded in 2023 while diving to the wreck of the Titanic, is a recent and brutal reminder. The Titanic sits at about 12,500 feet. That is dramatically less than half the depth of Challenger Deep. The Titan's hull failed at that depth. 5 people died in less than a heartbeat. Now multiply the pressure that destroyed the Titan by a factor of 3. That is what waits at the bottom of the trench. The lesson the engineering community has taken from these losses is sobering. The deep ocean punishes hubris. The materials, the design, the testing have to be perfect. Every weld, every bolt, every viewport. There is no margin for confidence not backed by data, which is why the very first time humans ever attempted to reach the bottom of the Mariana Trench, what happened halfway down nearly ended the whole expedition before it could finish. It was January 23rd, 1960. A bathyscaphe named Trieste was floating on the surface of the Pacific Ocean, somewhere above the Challenger Deep, with two men sealed inside its tiny pressure sphere. Their names were Jacques Piccard and Don Walsh. Trieste was a strange-looking machine. The crew compartment was a steel ball about 7 feet across, hanging beneath a long float chamber filled with gasoline. Gasoline is lighter than water and resists compression, so it served as the buoyancy material. To sink, the crew released iron pellets from above. To rise, they dropped them. Crude, effective, built to survive what was coming. The descent took almost 5 hours. The temperature inside the sphere dropped quickly. Both men sat in heavy clothing, watching gauges, listening to the slow ticking of their depth instruments. There was almost nothing to see out of the small viewport, just black water sliding past as they fell deeper. Around the 30,000-foot mark, something happened that neither of them was prepared for. There was a sudden, sharp crack. The whole vessel shuddered. The sound was loud enough that both men felt it through the steel of the pressure sphere itself. Piccard later wrote about the moment in his book. He described it as one of the most chilling sounds he had ever heard. A vessel built to survive the deepest pressure on Earth, halfway through its first descent, making a noise like something breaking. They did not panic. They did not have time. They checked their instruments. The gauges held. The sphere appeared intact. They were still alive. They decided to keep going. It was only later, after the vessel returned to the surface, that the crew discovered what had happened. One of the outer plexiglass viewports in the entrance tunnel had cracked under the pressure. The viewport was not part of the main pressure sphere, so the failure had not killed them. But the noise had been the entire vessel transmitting the shock of that crack through its structure. If the crack had been on the main sphere itself, both men would have been dead in less than a second. They reached the bottom around 1 in the afternoon. The depth gauge read about 35,800 feet. They were sitting on the floor of the deepest place on Earth, in a vessel that had just warned them how easily it could fail. The arrival itself was almost an anticlimax. The thrusters and the descent had stirred up a thick cloud of pale silt from the seafloor. Visibility through the viewport was near zero. They had reached the bottom of the world and they could barely see a thing. They stayed on the floor for about 20 minutes. That was all they dared. They radioed reports up to their support vessels using a slow underwater telephone system that took hours to transmit anything intelligible. They ate a chocolate bar each. Then they began the long ascent back to the surface. The whole world heard about the dive within days. It became one of the great achievements of 20th century exploration. 2 men, in a steel ball, had touched the deepest point on the planet and lived to tell about it. But Piccard came back with more than a record. He came back with a claim that would unsettle biologists for decades. He insisted, looking out through that silt cloud, that he had seen something move. Something with eyes. Something that should not have been able to exist down there. When Jacques Piccard came back from the bottom of the Mariana Trench, he carried a story that biologists are still arguing about more than 60 years later. He said that as Trieste settled onto the seabed and the floodlights cut through the silt cloud, he saw a flatfish. A creature about a foot long, shaped like a sole or a flounder, lying on the bottom and looking up at the submersible with 2 visible eyes. He watched it for several seconds before it slowly swam away into the dark. For Piccard, the sighting answered one of the biggest questions in deep-sea biology. Could complex life, vertebrate life with bones and eyes and active swimming muscles, survive at the absolute extreme of ocean pressure? His answer was yes. He had seen it with his own eyes. He wrote about it with conviction. The book describing the Trieste expedition spent pages on that single moment. The problem is that almost no biologist today believes he actually saw a flatfish. Here's why. Flatfish are bony fish. Bony fish have a swim bladder, a small gas-filled organ that helps them control their depth. At the pressure of the Challenger Deep, A swim bladder is impossible. The gas inside would be crushed to nothing. Any fish with that anatomy would be physically unable to survive at that depth, much less swim around looking comfortable. There's also no record of a true flatfish ever being recovered from anywhere near the depth Pickard described. Modern surveys have caught fish at extreme depths. The deepest confirmed fish, a kind of snailfish, was filmed alive at around 27,000 feet down. That is impressive. That is also still about a mile shallower than where Pickard claimed to have seen his flatfish. So what did Pickard actually see? There are several possibilities. The first is that he saw a sea cucumber. Some species of holothurian, the official name for sea cucumbers, can be flat, oval, and surprisingly mobile. A large one, briefly lit by submersible floodlights and seen through a foggy viewport in cold and exhausted conditions, could conceivably look like a fish to a tired observer. The second possibility is that he saw a kind of deep sea creature we have not yet cataloged. The trench is enormous. Most of it has never been visually surveyed. There could be entirely new categories of bottom-dwelling animals down there, shaped in ways we have not imagined. Pickard may have seen something real that we have never seen since. The third possibility, the one most modern biologists quietly favor, is that he was mistaken. Perhaps he saw a piece of marine snow drifting through the light. Perhaps he saw a shadow on the seabed that his brain interpreted as a familiar shape. Humans are very good at pattern recognition, especially under stress. The mind fills in gaps. Pickard never wavered. Until his death, he insisted he had seen a fish. And he had a point that is hard to dismiss. He was the one in the sphere. He was the one looking out. Nobody else has ever been in his exact position, in that exact moment, with that exact view. The skeptics are arguing from theory. He was arguing from memory. The truth may never be settled. Trieste's viewport was small. The silt cloud was thick. The lights were limited. And until many more humans descend to the same place, with much better cameras, the question of what lives at the absolute bottom of the trench remains partly open. What we do know for certain is that life is down there. Real, weird, perfectly adapted life. And the next person to actually film the deep floor in detail did not arrive for another 52 years. For more than 50 years after Trieste, no human went back to the bottom of the Mariana Trench. Not one. The dive was considered too dangerous, too expensive, too pointless. Robotic vehicles took over. They sent back limited footage and small samples. The deep stayed almost as mysterious as it had been before 1960. Then in 2012, a Canadian filmmaker decided to change that. His name was James Cameron. The same James Cameron who made Titanic. The same one who made Avatar. He had spent years quietly funding and designing his own deep submersible. He called it the Deep Sea Challenger. It was a vertical torpedo-shaped vessel, painted bright green, with a tiny pilot compartment at the bottom. He was going to fly it himself. Solo. The descent took about 70 minutes. Much faster than Trieste, because the design was newer and the buoyancy more efficient. Cameron sat alone in his compartment with cameras rolling. He listened to the hull groan as the pressure built. He watched his external lights probe the dark. He kept flying. He reached the floor at a depth of about 35,787 feet. Slightly less than Trieste's official depth, but in the same basin, on the same vast plain. What he saw was nothing like what Pickard described. There were no fish flapping past the viewport. There were no glowing creatures dancing in the light. The bottom of the Challenger Deep, according to Cameron, was a desert, pale, flat, almost featureless, a soft yellow-tan color where the silt had settled. Footprints of nothing, because nothing big walked there. No coral. No vents in his immediate area. No swarms of life. Just an enormous silent plain extending in every direction beyond the reach of his lights. Cameron stayed at the bottom for several hours. He used robotic arms to collect sediment samples. He filmed methodically. He kept hoping to see something move. Most of the time, he saw nothing at all. Occasionally, small creatures drifted through the light. Tiny shrimp-like amphipods. Pale, translucent, ghostly. Some appeared to be feeding on the seafloor itself, sifting through the silt for whatever organic matter had drifted down from far above. What struck Cameron most was the loneliness of the place. He described it later as the most isolated experience of his life. The closest other human being was on a ship miles overhead and 7 miles up. If anything went wrong with his vessel, no rescue was possible. He was as far from help as a person can get without leaving the planet. His samples turned out to be scientifically valuable in unexpected ways. Microbiologists who studied the sediment found enormous communities of microbes, vastly more than expected. Life at the bottom of the trench was not absent. It was simply concentrated in places Cameron's lights could not show. The seafloor was teeming with microscopic activity, even in the apparent emptiness. His footage also revealed something subtle. The seafloor itself was layered. Different colors of sediment indicated different ages of accumulated material going back thousands of years. The trench was acting as a kind of trash bin for everything that fell from the upper ocean. Dead plankton, shed shells, dust from far away. The bottom was a slow archive of everything that had ever lived in the water above. Cameron returned to the surface a different person. He had become only the third human ever to reach the deepest point on Earth, and he had brought back the first real high-definition footage of what waited there. But for all his footage, all his samples, all his hours on the seafloor, he had only visited a tiny patch of an enormous alien landscape. The vast majority of the trench remained, and remains, untouched. And it would be many more years before anyone else dared to follow him down. Almost 6,000 people have stood on the summit of Mount Everest. 600 and something have flown into space. 12 have walked on the surface of the moon. Only about 27 human beings have ever reached the bottom of the Challenger Deep. The exact number changes a little depending on who is counting and which expeditions are included, but it is shockingly small. Fewer people have visited the deepest point on our own planet than have orbited it from above. The deepest place on Earth is harder to reach, in many practical ways, than outer space. Why so few? The first reason is the equipment. Only a tiny number of vehicles have ever been built capable of reaching that depth. Trieste, Deep Sea Challenger, DSV limiting factor, and a handful of Chinese submersibles, including one called Fendoji. That is essentially the entire fleet, ever. A trip in one of these vessels, when offered commercially, cost a sum in the high 6 figures or low 7 figures per seat. The second reason is risk. Every dive carries a real chance of catastrophic failure. The pressure is unforgiving. The recovery time, if anything goes wrong, is impossible. There are no rescue submarines that can reach you. If your vessel fails, you are not coming back. Crews accept this knowingly before each descent. The third reason is purpose. There's genuine debate within the scientific community about whether sending humans down is even worth it. Robots can collect samples. Robots can record video. Robots do not need air, food, or warmth, and they do not die when the hull cracks. For pure data gathering, an unmanned submersible is more efficient and far cheaper. But humans keep going anyway. Why? Part of it is the same reason humans climb mountains and walk on the moon. Some places have a pull on the imagination that data alone cannot satisfy. To stand at the deepest point on Earth, even briefly, even sealed inside a tiny steel ball, is to experience something nobody else has experienced. The list of names is short. Each one becomes part of a small and exclusive history. Among those who have made the dive in recent years is Victor Vescovo, an American investor and explorer who reached the bottom of all 5 of the world's deepest trenches in a single expedition called the 5 Deeps. His vehicle, DSV limiting factor, has now made more trips to the Challenger Deep than any other crewed submersible in history. Vescovo brought paying passengers on some of those dives, including former astronauts and other adventurers. In 2021, the explorer Richard Garriott made the descent. He became the first person to have visited both poles, the International Space Station and the deepest point in the ocean. A small but real club of all-around extreme explorers. Chinese teams have been quietly increasing their presence at the bottom as well. The Fendoji, or Striver, has now made dozens of crewed dives to the Challenger Deep, conducting research that has produced significant findings about deep-sea biology and geology. The number of people who have stood on the seafloor of the trench will continue to grow, but slowly. Each dive is still a major engineering operation. Each one is still expensive. Each one still carries the chance that the hull will fail, and the vessel will become a tomb. When you imagine the deepest place on Earth, you should picture this: a floor that stretches for hundreds of miles in every direction, almost completely undisturbed, visited only briefly by a few small steel bubbles, lit, for just a few minutes at a time, by a handful of artificial lights. Out beyond the reach of those lights, in the dark that has never been seen, things move that no human has ever named. One of them looks like a slip of pink ribbon, and it has the deepest record of any fish ever filmed. If you went looking for the toughest fish on Earth, you would not pick anything that looks like the snailfish. It is small, about the length of your hand, pale pink, sometimes nearly transparent, soft to the touch, with no scales, no armor, and no obvious defenses. Its body looks like a sliver of jelly with a tiny head and a tapering tail. You could pick one up, if you ever met one alive at the surface, and it would feel like a piece of wet paper. And yet, the deep-sea snailfish is the deepest living fish ever recorded. Members of the family have been filmed swimming alive at depths of more than 27,000 feet. That is over 5 miles down. Crushing pressure, total darkness, near freezing water. The snailfish handles all of it. In 2023, a research team filmed a snailfish in the Izu Ogasawara Trench off Japan at a depth of about 27,349 feet. That broke the previous record for the deepest fish ever observed, set by another snailfish in the Mariana region. What makes them able to live where almost nothing else can? The answer is a chemical called trimethylamine oxide. It is a small molecule found in many fish, but in deep-sea snailfish, it is concentrated to extraordinary levels. The molecule props up the structure of proteins inside the fish's cells. At normal pressure, proteins fold themselves into the shapes they need to function. At extreme pressure, those folds collapse. Proteins lose their shape. The cell stops working. The fish dies. Trimethylamine oxide acts like an internal scaffolding. It forces the proteins to keep their proper shape even when the surrounding pressure tries to crush them. The deeper a fish lives, the more of this molecule it produces. By the time you reach snailfish at 27,000 feet, their tissues are saturated with it. But there is a limit. Researchers calculate that even trimethylamine oxide cannot protect proteins below about 27,500 feet. Beyond that point, the chemistry of life starts breaking down no matter how well adapted the animal is. That is why the deepest fish records cluster around the same depth, and why nobody has ever filmed a true bony fish at the very bottom of the Challenger Deep, almost 1.5 miles deeper. The snailfish has other tricks too. Its body contains almost no air. Its skeleton is partially cartilage rather than fully formed bone, which makes it more flexible under pressure. Its tissues are gelatinous, which helps them resist deformation. Even its eggs are oversized, giving the young extra reserves to survive in a place where food is scarce. How does a snailfish find food at all in such an empty place? The answer is patience and opportunism. The deep-sea snailfish swims slowly through the dark, hunting for tiny crustaceans called amphipods. The amphipods themselves feed on whatever organic material has drifted down from the upper ocean, including the carcasses of dead animals from the surface. When a whale dies and sinks, It can feed an entire deep ecosystem for years. The snailfish positions itself in that food chain like a quiet predator, picking off amphipods one at a time. Researchers have caught snailfish on baited cameras in nearly every deep trench they have studied. The animal seems to thrive in these isolated systems. Each trench may even have its own genetically distinct population, separated from neighboring trenches by stretches of shallower water that the snailfish cannot cross. That is a remarkable thought. Each deep trench may be a small world with its own snailfish lineage, evolving in isolation for millions of years. If the snailfish is the king of the depths, the swarms of pale, drifting amphipods are the citizens. And some of them, down in the Mariana Trench, have grown to sizes that should not be possible. In most parts of the ocean, amphipods are tiny, smaller than your fingernail. They are crustaceans, distantly related to shrimp and lobsters, and they form one of the most successful animal groups in the sea. Trillions of them drift through the water column at every depth. Most of the time, you would never notice them. But in the deepest trenches, something unusual happens to them. They get big, strangely big, disturbingly big. The Mariana Trench is home to amphipods that grow to the size of a large hand. Some specimens caught on baited traps lowered into the trench have measured over 11 inches long. That is a crustacean, roughly the dimensions of a small lobster, but with the body plan of a flea. Multiplied, pale, almost transparent in some species. Biologists call this phenomenon abyssal gigantism. It happens in many deep ocean groups. Squid get bigger. Isopods get bigger. Sea spiders get bigger. Animals that are normally small at the surface tend to balloon in size as you go deeper. Nobody is completely sure why. There are a few leading theories. One is that the cold, stable temperatures of the deep slow down metabolism, allowing animals to grow larger over longer lifespans. Another is that the scarcity of food rewards animals that can store more reserves and survive longer between meals. A third is that the absence of large predators in the deep removes the evolutionary pressure to stay small and unnoticed. Probably all three play a role in different proportions for different species. What scientists do know is that giant amphipods are common in the trench. Drop a baited trap into the Mariana, and within hours, dozens of these animals will swarm onto the bait. They are scavengers, designed to find dead organic matter and consume it as fast as possible before competitors arrive. In an environment where food is rare, speed and aggression at the buffet matter more than anything. Footage from baited cameras in the trench shows something almost disturbing to watch. A piece of fish lowered to the bottom is calm and untouched for the first few minutes. Then a single amphipod arrives, then another. Within an hour, the bait is invisible under a writhing carpet of pale, segmented bodies, each one the size of a bar of soap, clambering over each other to get a piece. Within a few hours, the bait is gone, stripped to bones. Sometimes the bones themselves are gone too. Researchers have studied the bodies of these giant amphipods carefully. They have found something unsettling. The tissues of trench amphipods contain unusually high concentrations of pollutants, specifically persistent organic pollutants, which are a class of human-made chemicals including PCBs and certain pesticides that have been banned for decades but never fully broken down in the environment. In some samples from the Mariana Trench, the levels of these pollutants in amphipod tissues were as high as those measured in heavily polluted industrial rivers. Higher, in some cases. The deepest place on Earth, far from any city or factory, contained some of the most contaminated animals on the planet. How is that possible? The answer is gravity. Pollutants released anywhere on Earth tend to bind to particles. Those particles eventually fall into the ocean. In the open ocean, they sink. They keep sinking. They drift down through every layer of water until they reach the bottom. The deep trenches act as collection points. Anything that falls into the ocean above eventually arrives in places like the Mariana. The amphipods, scavenging the bottom, accumulate the contamination in their bodies. The deep is not pristine. It is downstream from everything we have ever done, and the biggest single-celled organisms in the ocean live down there too, slowly straining the polluted mud for whatever they can absorb. In high school biology, you probably learned that single-celled organisms are microscopic, too small to see without a microscope. That is generally true. The xenophyophores of the Mariana Trench did not get that memo. A xenophyophore is a single-celled organism. One cell, no nervous system, no internal organs in the way we usually think of them. Just one giant cell, by the standards of its category. And in the deep trench environment, some species grow to the size of a dinner plate, up to about 8 inches across. That is a single cell you could pick up with your hand, if you were down there to do it. These animals, if you can call something with one cell an animal, build elaborate shells around themselves. The shells are made from particles they sift out of the surrounding mud, tiny grains of sediment, bits of dead microorganism shells, mineral fragments. The xenophyophore arranges these pieces, glues them together with proteins, and lives inside the resulting structure. The shells can take strange and beautiful shapes: fans, plates, branching trees. They look like miniature works of geometric art on the trench floor. The xenophyophore feeds by extending sticky strands out of its shell to capture passing particles, then pulling the food back inside to digest. It moves slowly across the seafloor, leaving little tracks in the sediment behind it. Compared to the active hunting of an amphipod, the life of a xenophyophore is almost painfully slow. Decades may pass before a single individual reaches its full size. Why are they so big? The leading theory is similar to the explanation for amphipod gigantism. The combination of cold temperatures, stable conditions, and slow metabolism allows xenophyophores to grow far beyond their normal size limits. There may also be an advantage to being large in a place where food drifts down from far above. A bigger surface area collects more falling debris, but xenophyophores are more than curiosities. They are ecosystems unto themselves. The shells they build are full of small chambers and crevices. Other deep-sea animals move into those spaces, using the xenophyophores' structure as shelter, food source, and breeding ground. A single large xenophyophore can host dozens of smaller organisms: worms, tiny crustaceans, microscopic larvae. The xenophyophore builds, the community follows. When a xenophyophore dies, its shell remains on the seafloor for a long time. The structure does not decompose quickly in the cold and the dark. New shells slowly accumulate over generations. Some areas of the deep trench floor are densely covered with xenophyophore remains, forming a kind of architectural layer above the mud. The trench is built, in part, by its own residents. Researchers have only begun to catalog the species of xenophyophores in the Mariana Trench. New types are discovered on almost every dedicated expedition. Some have body plans nobody has seen before. Some build shells out of unusual materials. Some appear to live in conditions that would kill nearly every other organism on Earth, in mud rich in toxic metals or in zones of unusual chemistry. The deepest known xenophyophores have been found at depths of well over 20,000 feet. They survive in places where temperatures hover just above freezing, where pressure is over 600 times what we feel on the surface, and where food is so scarce that some species may grow only a fraction of an inch per year. These are the patient kings of the deep mud. They have been doing what they do for hundreds of millions of years. Long before there were fish, long before there were vertebrates, the xenophyophores were already there, building their shells. And the very rocks they sit on may be part of the reason life exists on Earth in the first place. Near the Mariana Trench, in the deep waters along its edges, there are structures that look like underwater hills. Some are tall and broad, rising hundreds of feet above the surrounding seabed. Some are smaller, just gentle bumps in the bottom mud. They share one strange feature. They are not made of lava. They are made of mud. Specifically, a kind of mineral-rich mud called serpentinite. The hills are called serpentine mud volcanoes. They form when seawater seeps deep into the Earth's crust through cracks created by the movement of tectonic plates. The water reacts with rocks rich in iron and magnesium far below the seafloor. The reaction produces serpentinite mud. The mud expands as it forms. It is forced upward through the same cracks the water used. It eventually erupts, slowly and quietly, onto the seafloor. The result is a hill of soft, alkaline mud, leaking warm water and unusual chemicals into the cold dark of the deep ocean. There are dozens of these mud volcanoes scattered along the edges of the Mariana Trench. Most of them have only been mapped at low resolution. Some have been visited by submersibles and robotic vehicles. The ones that have been studied carefully turn out to be among the most interesting places on the planet. The water leaking out of a serpentine mud volcano is unusual in several ways. It is warm, sometimes much warmer than the surrounding seawater. It is highly alkaline, with a pH well above that of normal ocean water. It is rich in dissolved hydrogen gas,